Welcome to my study once again, this time for our discussion of the last chapter in the Giere book. The last chapter gives us some examples for applying the program that we're going to use. So the first thing we want to do is see how to use the Giere program, how to use the material that we have learned to this point, summarize it in terms of a program to follow in evaluating decisions, and then give an account of what to do and why to do it based on the kind of decision matrix we've been constructing throughout our decision theory discussions. So first we're going to look at the program very quickly and then evaluate it, use it with a couple of examples. First, we outline the 6 steps involved in constructing any decision matrix. The first step involves identifying the available acts or options. Second step, the states of the world. Third step, the outcomes. Fourth step, the values and utilities, depending on which you're doing. If you're doing expected value theory, you use monetary units. If you're using expected utility calculations, you use utilities. Then you identify various strategies that might apply to the situation that you've got. The strategies involve deciding whether it's a decision being made under complete uncertainty or whether you know something about the probabilities of the various states of the world. And then you give a summary of the evaluation with respect to the matrix that you've constructed. So a shortened statement of the program is: build the table, identify the available strategies for deciding what to do, and then summarize the results. With respect to identifying strategies, some decisions we make under complete uncertainty, and for that we have various rules that we've paid attention to. If there's a best strategy available, use it, where we understand a best strategy in terms of the first rule, the dominant strategy. If you can find a dominant strategy, use it. Second, if there isn't any dominant strategy, but there's a single satisfactory one, choose that option. If there isn't a single satisfactory option, perhaps there is a range of rational options somewhere. We're doing this, by the way, on a subjective basis. So this is about your sense of appropriate risk. So somewhere short of being a crazy gambler, maximize the maximum, or maximax, and the more risk-averse strategy of maximin, where you just pay attention to the minimums and try to maximize the worst case scenario for you. Somewhere between that will be a range of things, a range of options that make sense from your perspective. After we identify what makes sense from your perspective, we can have further discussions on whether your perspective is nuts or not. I mean, we do this with each other all the time. Somebody explains themselves completely and you say, okay, I understand now why you're thinking of doing that, but I'm sorry, that's just nuts. It's probably best if this is somebody you're really good friends with, because telling somebody they're nuts often ends a relationship, as I'm sure you're aware. So that's what's going on when we're identifying strategies under uncertainty. If we have known risks involved, so if we know something about the probabilities of the various states of the world, then we have a question on whether to model our decision in terms of monetary units or the more generic preference orderings involved in a utility scale. If the former, you use expected value strategy. If the latter, you use the expected utility strategy. So let's apply this program to a couple of examples. The first case will be one where there's low causal effectiveness at work in the problem. So people have worried ever since oral contraceptives were first introduced about the risks of taking them. This is something worth worrying about no matter what drug you're taking of any sort, prescribed or not prescribed. But in any case, you got to worry about the risks. What are the side effects of the drug? And one of the worrisome concerns was that oral contraceptives cause breast cancer. So here's the data that we're going to use. 1 in 500 get breast cancer among those using the drug for 4 years or less. This is sort of coarse-grained data, but let's suppose it's all we've got to go on. All we know is the percentage for people that use it for 4 years or less, and those who use it for more than 4 years. The number is a bit higher. So 1 in 300. So here, available acts, it's obvious. You can use it for 4 years or less, including never using it at all, or you can use it for 4 years or more, and the states of the world are two. Either you get breast cancer or you don't. The outcomes are the 4 possible combinations of states and acts, and the values are utilities here. Which one shall we use? If we measure utility on a 0 to 1 scale, we should expect the following kinds of results. The worst outcome would be using oral contraceptives less and still getting breast cancer. With the other breast cancer outcome very close to it. Taking the pill more and not getting breast cancer, let's assume, is the most preferred option, with the other no breast cancer outcome close to it. So they're not spread evenly through the 0 to 1 scale, but 2 of them are very high and 2 of them are very low. So suppose we represent it this way. Note that we're making things up here. We're saying 2 of the cases are clustered near the bottom, 2 are clustered near the top, so we're just going to represent them with numbers that are very close. There is a worst outcome always when you do utility scales. When you identify the outcomes that are relevant, you put your best outcome at 1, your worst outcome at 0, and then you try to measure in some way or another, either with the Ramsey method or the more modern utility theory of von Neumann and Morgenstern. You try to calculate how far away from the best and worst the remaining options are, the remaining outcomes are. So let's suppose that you end up with these numbers. So you did the measuring and you ended up saying this outcome is that close, very, very close to the worst outcome, and this outcome is very close to your best outcome. That reflects the fact that the most important thing here, represented in our table, the monumental factor here is whether you get breast cancer or not. Presumably, whether you take the pill or not, maybe there's some advantages of taking the pill, some disadvantages of taking the pill, but the difference between taking the pill and having to do something else instead is incredibly insignificant compared to whether you get breast cancer or not. So that's what our table reflects. Since we know the risks here, that's what the 1 in 500 and 1 in 300 numbers gave us, we can use the table to generate an answer using the expected utility formula. Notice that the table in question is constructed using utilities rather than monetary units, so the question of whether the monetary value adequately represents utilities doesn't arise for this case. So we multiply the second row and the first row by the relevant pieces of information we have about the known risks, and that generates the following table. So you look at this table, you know that that number is going to be 0. This number, if you get out your calculator, turns out to be 98802, and so depending on how many decimals you want, you go out that far. This number is pretty easy. This number is 0.00, how many zeros do we have to go out? We need 4 zeros. Very tiny numbers, so you add this one and add this one. That's not quite right. You gotta have a few more zeros, right? In any case, you'll get roughly 0.997 for the top and 0.988 for the bottom row. And then let's hope you're not as bad as I am at reading the table. So I left this in place because it's a mistake I made. I just read the table wrong. Can you tell which of those two numbers is bigger than the other? Obviously, the top number is bigger than the bottom number. So the decision matrix in place here says, yeah, I know taking the pill increases your risk of breast cancer, but not enough to matter. So I said it recommends not taking for more than 4 years. That's not correct. I just misread this number, this bottom number here, as 0.9988, which it isn't. So I left the mistake, and I will now cross out the mistake here just for fun. Not for fun crossing it out, but I left the mistake there for fun because one of the worst things you can do is misread the table after you did all the work to build it properly. Now notice after this sentence is negated, what follows is the right way to think about this. This result assumes a certain level of risk tolerance, one that's encoded in the utilities. So the 0 in 1 is fixed, but the question is, how close are the other two to these extremes? We made a certain assumption when we got that, and maybe that assumption is mistaken. It's interesting to look at this table and figure out what kind of changes in our utility scale would lead to a reversal so that what I wrote would be correct, that a table recommends not taking oral contraceptives for more than 4 years. How would these two numbers have to change in order to flip the decision that you're making from the table that results? Here's another example. This has a more moderate causal effectiveness built into it. So it's about smoking and life expectancy. So we're talking about life expectancy for somebody who's a 25-year-old male who smokes a pack a day. And you're wondering what your life expectancy is in question for living up to age 65. And we have some data. 38% of smokers die before age 65, 22% of non-smokers. So we now know something about the probabilities involved in the table we want to build. So we build a table. Our two acts are to smoke or not to smoke. The states of the world are die before 60 or not. So we get a little matrix with 4 possible combinations. Now, in our outcome spaces, we have to say something about values or utilities. We don't know the monetary values, so let's try to estimate utilities here. That's a little bit complicated since you might not like smoking. If you don't like smoking, I think your decision is going to be really simple. So let's assume that you do like smoking, otherwise you wouldn't have a decision problem. Assume then that you prefer to smoke. So the best outcome is to smoke and live a long life. Let's also suppose you want to live a long life. That not all people want to do that, but let's just assume that you do. And the worst is to give up smoking but die young anyway. So let's assume the same closeness that we saw in the last example. So your worst outcome is don't smoke and die. Your best outcome is smoke and live. So those are the 0s and 1s. And then as before, we assume dying is way more significant for you than whether you smoke or not. So we assume dying before 60 on the assumption that you're smoking is pretty close to the worst, but not quite as bad as having to give up smoking. And living to a ripe old age of some sort over 65 is good for you, but not quite as good as doing the same thing and getting to smoke at the same time. Okay, now we have the matrix in front of us, and we also know what the probabilities of each of the outcome spaces are. That was what the 38% and the 22% generated for us. So you put in the 38.38 for smoking and 0.62 for surviving to 65 or older, and 0.22 for dying early if you don't smoke, and 0.78 if you do. Then when you sum the numbers, those are the results. Now, the fact that the causal factor involved is a bit more significant in terms of the differences here leads us to a different outcome than we had last time. When there's only weak causal significance, as in the case of taking birth control pills and getting breast cancer, taking the pill, even though it's a risk, wasn't enough to make giving up pills before 4 years the rational thing to do, at least with the utilities that we had on the scale. Here, because the causal factor is more significant, we end up with the calculation telling us not to smoke. And the explanation that the difference between this and the last case is the causal effectiveness of the bad thing that you're doing. Once again, you might be able to reverse this answer based on how much you care about dying early versus not dying early. So how close, you might still prefer not to die early, but these numbers in the circled outcome boxes might not be as close to the extremes as we're modeling them to be. So you should be able to calculate what kind of changes could occur to those boxes that would reverse the decision on whether to smoke or not smoke. Here's a public policy decision, and this is our last example. So this is an example comparing global warming with the Cold War issue of whether to arm your country with nuclear weapons or not. So after the 1960s, and actually during the 1960s, there were people that called themselves peaceniks, and they said, we should just disarm. The country should not spend any money on nuclear weapons at all. Now, in both of these cases, the global warming and the Cold War question of whether to spend a lot of money making nuclear weapons, the best and worst outcomes are easy to identify, and it doesn't much matter how far away from the best option we treat each intermediate outcome. So in both cases of policy decisions under uncertainty, the tables corresponding to the first 4 steps of the program look like this. So the first table is the contrary argument. People said, better red than dead. That would be the peacenik view. And the slogan is making fun of the hawks who said better dead than red. That's what the slogan was. Nobody had this as a slogan, but they did have the slogan where the red and dead changed places. So we can either disarm or arm. And in the case of global warming, we can either do nothing or try to stop it. And then the states of the world are either war or no war will occur. And either global warming will kill us all or something else really nasty, or it won't. So let's just put that down as either warming will continue or it'll just quit. So you have 2 decision matrices, and notice what dominance reasoning does for you here. You don't need to know anything about the probabilities or anything like that, because dominance says doing nothing if warming occurs dominates doing something, and doing nothing if no warming will occur also dominates do something. Similarly, either there's going to be a nuclear war or there's not. And if there's going to be a nuclear war, disarming beats arming. And if there's not going to be a war, saving money beats spending the money to arm. So notice the numbers are not going to matter much here. You're still going to get dominance reasoning favoring doing nothing, and disarming. But here's the kicker. Notice that the probabilities of war and no war are not independent, or at least are not known to be independent of the issue of whether we arm or disarm. Because the people who say we should spend money on nuclear weapons say, if we don't, that enhances the chances that somebody's going to use them against us, right? So the deterrence argument here tells us the states of the world are not independent of the actions in question. Similarly, you can say the same thing with the bottom one. Doing nothing or doing something affects the probability of global warming continuing versus halting. This is the most crucial thing to think about when you're thinking about applying dominance reasoning. Dominance reasoning is perfectly good reasoning when the states and acts are independent. It is not good reasoning when the states and acts are not independent, because then you will get probabilities in each of these boxes that play a significant role in affecting what you should do, just as they did in the non-smoking case and the birth control pill case as well. So the crucial thing to remember is don't resort to dominance reasoning to evaluate a case unless you're very confident that the states and the acts are independent of each other. So remember, our usual case for dominance reasoning has to do with, we did matrices where you've got an urn with two colors of marbles in them, blue and green, and you can place certain bets. So you can bet on, let's say, green, or you can bet on blue. In these kinds of cases, notice your bet, the actions and states here are known to be independent of each other. How you're betting doesn't affect the percentage of blue and green marbles in the urn. So in that sense, the examples that we use to motivate decision theory and dominance reasoning may be a bit artificial, because it's fairly common, as in these kinds of cases, when it comes to really important, monumentous choices that we're making, the states and the acts are typically not independent of each other. The lesson then is, be careful when you engage in dominance reasoning. It's really good reasoning as long as you're confident that states and acts are independent. It's not good reasoning when they're not independent. Then you absolutely must factor in what the conditional probability of the state is given the relevant action that's performed. So you can't just say, well, there's a 0.7 probability of war. That's my pessimistic outlook on the future of the world. Human beings like to kill each other. So let's just say probability of war is 0.7, probability of no war is 0.3. Well, that sums over the probabilities that depend on what we do. If 0.7 remains the same, whether we arm or disarm, then we have independence and we can do that. But when they're not independent, you don't get to use the 0.7 number in both of these outcome spaces. Similarly, you don't get to use the 0.3 number over here. You have to use the conditional probabilities that are relevant. So here, you would multiply your utility times the probability of war given that we disarm. And if the deterrence argument is any good at all, it ought to be higher than the probability of war by itself, not conditional on anything else. For the second one, it doesn't actually matter what probability number you put in here, because this is our worst outcome. So 0 times anything is still going to be 0. But it will matter for box number, call this 1, 2, 3, and 4. It will matter for box 1, and similarly for 2 and 4. The only one that it doesn't matter for is 3, because 2 will not, even if this was 0.3, we don't have any reason that either box 2 or 4 should be a 0.3 number either. That's a well-known defect of dominance reasoning. So if somebody offers you a program and says, look for dominance reasoning first, always look for it first. If you find it, you're done. That is the case when you don't know anything about the probabilities, because if you know nothing about the probabilities, you can't take into account the dependence of the states on your actions. But even if you know something about the probabilities, if you know independence is present, you get to apply dominance reasoning and then stop. But that's generally a risky thing to do because independence is rarely a satisfied condition.